All right. Get things started. Welcome, everybody, to the fall 2018 version of the TWed Lightning Talks. A little bit of logistics. We are streaming live on the interweb and recording for posterity. Your talks will be linked to from the Tetherless website. Actually, there's no questions tonight, just each of you getting up here and just talking about whatever you want to talk about for 2 minutes. Try to keep it to 2 minutes. Usually that's pretty easy to do. Your intuition guides you pretty well. When people finish their talks, give them a round of applause and appreciation the way that you would like to be appreciated. And then you can give yourselves a big round at the end. All right, without further ado, we will be working down the list. You can cross off yourself if you want to, or I'll catch you. And just be ready to go when the person in front of you finishes. And we'll start off with Sabir. Rock and roll.
Hi everyone, I'm Sabir Rashid. I'm a PhD student working with Deborah McGinnis. So the kind of research we do deals with the semantic web. So, and the language of the semantic web is this resource description framework, and there's many different syntaxes. So why do we want to represent knowledge as RDF? Well, it lets us annotate concepts and give rich definitions, comments, labels, all that stuff. It also lets us create this hierarchy of how concepts are related to each other, as well as how they're related to other concepts through properties that aren't subsumption based. And it lets us do this cool thing where we can infer new knowledge, right? So how do we do inference? Well, there's various rule languages, OWL being the most popular one, I suppose. But there's also this other language called Swirl. And what's cool about Swirl is that it lets you do kind of if-then statement. So if this pattern in my graph exists, then I can infer that this other pattern should also exist. What's not cool about Swirl is right now, if you want to, at least from my experience, in order to actually inference over Swirl rules, you need to use something like Protege, which has a pellet reasoner. And it's been hard because you need all the concepts that you define in your Swirl rule to be explicitly defined in everything else. So how else can you do if-then statements if you don't want to use Swirl? Well, you can use why-is, where you can write custom rules, which pretty much you say you define a graph pattern you want to match and a graph pattern you want to construct. And you can just run it through this kind of Sparkle-based reasoning type framework where it just constructs the new knowledge based on the patterns you're looking for. So that's one way to do special purpose reasoning, is to use why-is.
Okay,
thanks.
Thank you.
Hello, my name is Matt Johnson. I'm a PhD student in Deborah's research group. Here, I'm going to talk a little bit about a problem I'm working on. I'm looking at mapping data attributes from data dictionaries to a given ontology. I'm currently, this process will allow us to automatically generate semantic data dictionaries and more easily integrate new data sources into different projects. So we've been looking at applying a natural language processing technique developed by Hung's research group to generate local embeddings for words. We identify keywords within class definitions and also data dictionaries themselves. And then for each of those keywords, we find the context words around them that manipulate the meaning of the word slightly. We do this using abstract AMR parsing and find mappings to global vectors, such as glove vectors. Then we concatenate all these vectors into a giant vector and use an autoencoder to learn a smaller subspace. In this subspace, we then hopefully will find things with similar semantic meaning. So far, we've applied this technique to the terms within the SCIO ontology, and we've found we've performed some sanity checks and found like terms such as one-dimensional Cartesian coordinate. Their nearest neighbors are another, obviously, one-dimensional Cartesian coordinates, and then 2D and 3D respectively, along with other terms that quantify things within dimensionality. So, which is a good test, good case. Our next steps are going to be to apply this to actual data dictionaries and find meaningful mappings. And then hopefully, if these experiments work out, we will continue to apply them and integrate them into other frameworks such as Hot Attack to automatically suggest ontology mappings. And I think that's all I got. So,
All right.
A little quick.
Thank you. And if you noticed, each time you made reference to one of these other pieces of research, there was a footnote that would pop up.
All right. Hi, everyone. My name is Yarda Neiman. I am a co-terminal student under Deb, doing my master's this year. So a little bit of what I am going to be doing next semester, because I'm kind of just starting off. I'm going to take a look at a survey of semantic data portals. So when we talk about things like Hat Attack, which is, one of the frameworks here that we've developed for data ingestion and storing different types of data, is how we leverage the semantics in order to store this data, so that way we as researchers can get more out of the data that we have stored. So there are more things out there like Hat Attack. We want to understand what things exist, how semantics are being used in these other platforms, and what other things they might leverage. So I'm basically going to start off by defining what it means to be a data portal. Because to me, a data portal is something that, I can pull up the data in my web browser and kind of look at that. But to other people, it might just be a repository where you can download files. So establishing this definition of what it means to be a data portal as opposed to a data store or a data repository. And then looking at what other things exist, specifically in the medical and bio domain, although there are other domains that use this type of stuff. There's actually some semantic portal out there for journals, for journal entries that I've come across. So understanding that and then applying basically what exists out there to this definition to get a feel for what's in the field, and specifically for what we're doing that in Hat Attack specifically that aligns with this definition of a semantic data portal and what leverage that gives us. So that's what I'm going to be looking at.
Hello, everybody. My name is Kara Reedy, and I am a fourth-year PhD student working with Dr. Jim Hendler. My current research project is the same that it has been for the past 4 years, which has been that I am programming an artificial life simulation, which is full of these agents, which are controlled by neural networks, which are created by a genetic system. Now, usually when we do genetics in computer algorithms, we do something called haploidy, where we only have one copy of the genetic material. This system is a little bit weird and different because it uses diploidy, where it has 2 copies. So one thing that I've been doing is that I'm comparing diploidy and 2 different instantiations of diploidy with haploidy to see what sorts of advantages it might have, and I did get some kind of interesting results there. But something else that I'm moving towards is that eventually I want to do something with this simulation that could say something about social discrimination and both the social and genetic factors that could be in play during discrimination. So I'm still figuring out exactly how that's going to look. I'm thinking of how I could see the emergence of things like tribalism or subpopulations. And I'm starting off with something much simpler, which is that I'm giving the agents different ways to decide what family means, and then dissuading them from mating with their own family members to see what kinds of genetic effects that might have on the population.
Sorry, I missed your talk. You missed a few weeks ago.
I really want to say
Yeah, good check it out. Thank you.
Hello, everyone. My name is Hal. I'm a fourth-year PhD student with Professor Fox. That's me, right?
Rock and roll.
Since this summer, I've been working on a project working with Professor Johnson Samuel from Material Science Department. I've been working on creating a additive manufacturing processing ontology, which is used to represent the processing data created during the additive manufacturing process. There are several goals in creating this ontology and use that ontology to annotate the data and to store in RDF format. One is by creating a domain ontology, it allows us to reconcile data heterogeneity when we are trying to combine data from different areas. But more importantly, the future of our work is to try to create an augmented augmented intelligence system for additive manufacturing that can give researchers and experiment personnel suggestions in doing experiment. For example, we want to know under what kind of processing conditions can they create product of certain properties, and by the ontology work, it serves as an enabler for our future work to be able to encode these data into RDF graphs, which can also be seen as the foundation for reasoning, because the data are encoded in a statement. And that's for this semester. I have finished creating this ontology, which have a couple of features. For the time constraint, I won't go over it. But I'm also writing a master's thesis document describing the work that have been done so far from the summer to this point, and which I might give another presentation at some time. That's it. Thank you.
All right. Thank you.
Hi, I'm Shruti. I'm currently a master's student under Professor McGinnis, and some of the work that I started from the summer, and some of the work that I'm currently pursuing is basically semantic modeling of cohort descriptions. So what are the cohorts exactly? So basically, cohorts are a term to describe a group of people who share a set of common ranges for some of the attributes. More specifically, when the term is applied to a group of patients utilized within a research study. The term is basically used to summarize the set of attributes of a group of patients, differentiated by basically intervention, control, or basically outcome. Cohort descriptions are basically useful for the physicians whenever they're seeing some complex patients, and the physicians might want to ascertain the fit of a patient to the population utilized in these studies. So far, the work that I've done from the summer and this semester is to be able to build the ontology to encode the vocabulary used within the cohort descriptions, and using this ontology, some of the descriptions have been represented as knowledge graphs. In the future, using these knowledge graphs, we plan to drive the querying and inference capabilities to be able to determine the applicability of a patient to a particular study. Our end goal is to be able to build a framework to semantically extract, transform, and load cohort descriptions from research studies in a manner that we can drive the deep dive visualizations and similarities.
Thank you, Sophia. That's you. Still you.
Hi everyone, Corey, fifth year PhD working in Peter's group. This past summer, I did an internship at IBM Research Lab, and the topic is the legal judgment prediction. So we have a very large data set, which contains around 2.6 million samples of criminal cases. So the input is like a natural language description of a criminal case. So somebody at this date did this bad thing or something like that. And so the task, there are three tasks. The first one is to predict, to find the relevant law articles. The second one is try to find the charges. The third one is try to assign the prison terms to this case. So for the first two tasks, we converted into multi-label classification problem, and the third one is the regression problem. So we tried many different kinds of deep learning models, and eventually, I think the residual neural network, that one achieved the best result for us. Thank you.
Speak all the way to the back of the room.
Hi, I'm Neka Agu. I'm a second-year PhD student under Professor Jim Handler. I'll be talking about I'll be talking about my research on Hughes project, which is extending DMTO with gprob and temporal reasoning. So guideline provenance is a way of like adding a provenance to a rule and the guideline to show of the physician where the rule that generated a recommendation was obtained from. So clinical practice guidelines usually like give physicians a recommendation based on the patient's description or the patient's data, and most of the decision support systems don't give provenance of that information to the physician. So my work is basically linking the data, like the rules, to the provenance of the obtained from the guideline. Also, I want to add some form of temporality to the DMTO data, which is diabetes mellitus treatment ontology, and it's going to like be able to follow the patient's data, like the patient over time, to see at a given point in time if a patient transitioned from monotherapy to dual therapy. If the system suggested that a patient should move from monotherapy to dual therapy, did the physician follow the recommendation? So it's going to be able to highlight to probably physicians or to higher organizations whether a physician was following the guideline for a given patient, or if the physician never used the recommended treatment for a patient.
Thank you.
I'm Xiaoman from PhD student from Hengji's group. Currently, I'm working on cross-lingual word embeddings. So word embeddings essentially are vector representations for word. So word embeddings are usually learned from large monolingual corpus. So the goal of this work is to merge word embeddings from different languages into one single shared semantic space. The idea is very simple. So given a set of word embeddings in a source language and a set of word embeddings in a target language, and a set of pre-aligned words usually come from a dictionary, we can use this pre-aligned words as anchor to learn a linear mapping, which is able to transform the source language embeddings into the vector space of the target word embedding. So having done that, we can directly compare the similarity between words from different languages. So we apply the proposed embeddings to downstream application NLP applications, cross-lingual anti-linking and machine translation. So experiments results shows the proposed embedding significantly advance the state of art for both tasks.
Thank you very much.
Hello, my name is Hao Zhang, and I'm from TWed's group. I'm a 5th year PhD student approaching to the end of my PhD program. And for the final year, I'm working on memory network to extract events from the doctext documents. Traditionally, when we prepare, for example, event extraction data set or machine learning data set, we need a very long time to do annotation. Actually, we first define ontologies for the labels. Then we collect the data. Then we do education. We educate the annotators. You should do this. And then we ask them to annotate. Finally, we need to do quality control. That we do adjudication. But this takes a very long time. For example, there's a very famous benchmark data set. It starts from like 2002. And the final version is released in 2007. That's 5 years, and a PhD is already graduated, right? And so what my idea is, in the future, when we do the data set release, we do streaming version. For example, in ACE data, we have 600 documents. They take 5 years. So can we, for 60 months, every month we release 10 documents with fully annotation. And we use this as a model of streaming. However, there's another problem is in the early stage, the annotators made some mistakes. For example, they misunderstood they just misunderstand the ontology or the definition. For example, if they want to annotate something like the GPE, the geopolitical entities, for example, city, Troy City, or like New York State, but they may locate them as annotate them as location. Then there's a mistake for their understanding. And maybe in the later streams, they may correct them. But the early data set was already there, they do not revisit. So we use the memory network to memorize these mistakes, to know that, okay, these are mistakes, we should avoid them in the current streaming line. Then this is how my model works. Say I have a unified model to extract the information, and I have a memory network to know the abstracted features from the past documents. And I only work on the current raw documents of the current stream, then to improve the performance of my, for example, event extraction or other information tags. That's what I'm doing. Okay, thank you very much.
Thank you. Thank you.
Hi, my name is Kevin Blissett, and I'm a PhD student in Hung Ji's lab. And I think when you give a lightning talk, it's kind of good to have one point and just to make that point. So my one point is it's worthwhile to keep your mind open to things that are going on outside of your own narrow field of research. The things that I'm working on right now are kind of inspired by something I think is kind of remarkable happening in our lab, which is we work on low resource languages a lot. And we also require a lot of annotated data. And unfortunately, those two things don't work together very well. So something we've been doing lately in our lab is we'll be working on a language like Oromo, where it's difficult to find a speaker of that language. So instead of finding a native speaker to annotate that document, We just have non-native speakers annotate the document. And it turns out you can actually do pretty well doing that, because if you have parallel sentences, for example, and one of the sentences has the name George in it, and the other sentence has the name Jorge, a human's pretty good at saying, oh, these look kind of the same, and these are probably the same, and you can annotate it that way. So I was really inspired by that. I wanted to build a model that could kind of capture the idea of these two names look kind of the same, right? Which ones look kind of the same in a sentence. But although that's easy for a human to kind of intuit, that's a really difficult thing to say algorithmically what that looks like. So I was really struggling with this problem and thinking about, okay, well, how do you capture when words kind of look the same across all your languages and that kind of thing? And I couldn't come up with a good solution until I was thinking about kind of a different problem. And I started to think about the words almost as people. And it's kind of like you're just looking at different versions of the same person, right? And I thought about face recognition and all these cell phones and things, right? And that's exactly the problem, right? Is that you give them one picture of a person or a face, and then you give them a different face, and you say, do these faces look kind of the same? And so I thought, well, maybe I'll look at the face recognition literature and see if there's anything there. And it turns out there is, and it's directly applicable and kind of solves this problem, right? That the same technologies used to say, do two faces look the same, also can apply to, are these two names likely to refer to the same person? So yeah, my takeaway is just that I wasn't able to solve the problem until I thought about something outside of NLP entirely. And so that can be worth doing. And thanks.
That's a good thing. You talking.
Hi, my name is Andres Vargas, and I'm a graduate student under Professor Bennett. And my research has to do with data that I was given at the beginning of my research here from a semiconductor manufacturing plant. And we're thinking of the data as a 4-dimensional array indexed by tool, sensor, step, and wafer. And so when you index the array with these 4 indices, each index contains in it a time series. So what I'm doing is I'm algorithmically determining a summary statistic for each time series in this array. And that summary statistic can then be used for anomaly detection. So we have a procedure where you assign an anomaly score to the summary statistic, and then based on that anomaly score, you can detect anomalies in your data, which is important for fault detection in this manufacturing process. In addition to that, the summary statistic that we compute is also interpretable from a domain knowledge perspective, because its elements, if you think of the summary statistic as a vector, its elements are directly mathematically tied to the underlying feedback control system. And so what this means is that since we're detecting anomalies as a function of a summary statistic, and that summary statistic is mathematically tied to the underlying feedback control system, then we can mathematically, analytically tie the anomalies back to something that has physical meaning, and that has not been done before. Thank you.
Get everybody? I think so. Did you want to say something? Go ahead. Well, first, I just wanted to, everybody give yourselves a round of applause. How many people was this your first lightning talk? 3, 4? Oh, sorry. Yeah, it was your first TWed lightning talk. How about it was your second? Your second here? And your third? And your third here? Yeah. Your fourth? Tata left already, didn't you? I was going to go 5th. So I thought you're right there. But great job, everybody. I mean, this is a really diverse set of projects, and that's what's really cool about lightning talks is just that 2 minutes a shot here of all the diverse things that people are doing, and it's really fantastic and a great job. I know for some of you it was the first time, you might have been a little nervous, but it was awesome all the way around. Did you want to say?
Yeah, just wanted to add, we really appreciate you coming at the end of term. It's it's important to listen to what your colleagues are doing, and actually, I like having points, think outside the box. Lots of times that is the way you get some intuition to solve some research problem. And it was really fun listening to all of you, and I hope you all have happy holidays.
and finish off the food.
Oh, yeah, finish food.
Thank you very much.